Welcome to ROHM's laser diode and VCSEL product overview. Today we will cover our latest laser diode product lineup and feature set, as well as our vertical cavity surface emitting laser, also referred to as VCSEL, low power and middle power lineups. Let's begin with the introduction to laser diodes and VCSELs. Let's start with the definition of a laser. Laser stands for light amplification by stimulated emission of radiation. A laser diode is a light-emitting diode, LED, that is amplified by two reflectors. Depending on the position of these reflectors, the lasers can be divided into two types, FPLDs and VCSELs. Let me explain these figures. First, the figure on the left is an FPLD, or Fabry-Perot laser diode. It has a reflector perpendicular to the emitting area, and the light is emitted from the side. It is the thinnest and strongest of the three types. The figure in the middle is a VCSEL. A reflector is attached horizontally to the light emitting area, and light is emitted from above. The figure on the right is an LED. The light spreads out from the light emitting area. VCSELs have characteristics intermediate between FPLDs and LEDs and emit light that is aggregated to some extent. This table shows the technical comparison between an FPLD laser diode, a VCSEL, and an LED. Compared to an LED, the laser diode and VCSEL are superior in terms of beam divergence angle, light conversion efficiency, and response speed. Now that we've discussed the differences and compared these products, let's continue with a deeper dive into laser diodes. This roadmap shows the broad spectrum of our lineup going from laser diodes all the way to VCSELs and some of the various applications that are associated with each. We have different part numbers signifying the differences in emission width and optical power. The packages available include can type, surface mount, and bare chip. Some are still under development, but samples are available for all today. In this graph, we summarize the devices required in the LiDAR market. For automotive applications, at the right there, a detection distance of 100 meters or more is required, so a compact, high-power laser is needed. ROHM's high-power laser diodes have four features when compared to the competition. The first is a narrow emission width, which contributes to long range and high accuracy for LiDAR modules. The second is high PCE, or power conversion efficiency, which contributes to energy savings and high reliability of LiDAR modules. The third is low wavelength temperature dependence, which also contributes to energy savings and long distance for the LiDAR modules. The fourth is uniform light, which contributes to the high precision of these LiDAR modules. These features are explained in detail on the following slides. First, let's look at the narrow emission width. This table shows the optical output and near-field pattern, or NFP, width of each ROHM laser model. Two width values are reported, the width of the total light and the width of the FWHM, or full width height maximum, which is half of the peak intensity. ROHM's high-power laser diodes are available in 25, 75, and 120 watt classes with a pulse width of 50 nanoseconds. The emission widths are 50 microns and 70 microns for the 25 watt class, 225 microns for the 75 watt class, and 270 microns for the 120 watt class. ROHM has the narrowest emission widths in the market. In addition, ROHM laser diodes can be used at even higher maximum optical power, depending on the pulse width conditions in which they are driven. Under conditions of 15 nanoseconds or 5 nanoseconds or even less, which is even shorter than the 50 nanoseconds specified in the specifications, it is possible to use up to 1.5 to 3 times higher optical output power. The narrower the pulse width, the narrower the emission width of the laser diode that can be selected, thus improving the measurement performance of the LiDAR system. The second feature, high power conversion efficiency, is explained here. ROHM's high-power laser diodes have achieved a significant reduction in drive voltage, VF. The top two graphs show the current on the horizontal axis, the optical output on the left vertical axis, and the voltage on the right vertical axis. The left graph shows the characteristics of a conventional laser diode, while the right graph shows the characteristics available from current ROHM products. Converting this data to the bottom graph of current on the horizontal axis and power conversion efficiency on the vertical axis, we can see that we have succeeded in improving the PCE by 30% compared to the conventional method. This PCE is the best value on the market today. Because of the high PCE, the same optical output can be driven with lower power. This contributes to energy savings and higher reliability for LiDAR modules. Let me now explain the third feature, small wavelength temperature dependence. ROHM's high-power lasers have a wavelength temperature dependence of 0.15 nanometers per degree C, which is smaller than the competitor's wavelength temperature dependence of around 0.25 nanometers per degree C. This means that, for example, when the driving temperature range of a LiDAR is between -40 to +85 degrees C, ROHM has a wavelength shift of about 20 nanometers, while the competition shifts about 30 nanometers. The large difference in shift means that they are more susceptible to the effects of sunlight. ROHM's high-power lasers have a small wavelength temperature dependence, so the wavelength range of bandpass filters can be narrowed. ROHM's laser diodes can also reduce the effects of sunlight, which improves the signal-to-noise ratio. In other words, if the distance is the same, the optical output can be reduced for lower power consumption, or if the optical output is the same, the measurement distance can be increased. Let's now discuss the fourth feature of ROHM technology, uniform light. The upper two graphs show the cross-sectional light intensity distribution of the luminescence. On the left is ROHM's conventional product, and on the right is the new RLD90QZW3. ROHM has achieved this improved uniformity of light due to the unique structure of the laser element. The graphs on the bottom show the IL characteristics and the power conversion efficiency. By improving the uniformity of the light emitted by the laser, ROHM has succeeded in further improving the power conversion efficiency. This slide is an overview of ROHM's high-power laser. The RLD90QZW3 is a 905 nanometer, 75 watt, 225 micron emission width can-type laser. Its features include excellent wavelength temperature characteristics, low VF, and narrow emission width. Target applications for this device are LiDAR units for cars, automated guided vehicles, and cleaning robots. Using ROHM's lasers, the sensing distance and accuracy can be improved. Now let's jump into a discussion of ROHM Semiconductor's VCSEL technology. Here is ROHM's low-power VCSEL lineup. The model RLD94CHQF is a 6 milliwatt, 940 nanometer bare chip VCSEL. Its target applications are TWS, or True Wireless Stereo, digital still cameras, and smartphones. It is used as a light source for proximity detection and object detection. Models RLD85SAY6 and 94SAQ6 provide 200 milliwatts of optical power at either 850 or 940 nanometers in a surface mount package type. The target application is one-dimensional TOF, time-of-flight systems. Next, let me introduce the features of ROHM's low-power VCSELs. Our low-power VCSELs feature a single lobe. As shown in the lower left picture, conventional VCSELs have a donut-like optical shape. In contrast, ROHM has achieved a Gaussian beam shape by making the light uniform with its unique structure. Next, let me explain the upper right section. ROHM's 6 milliwatt class is ideal for proximity sensors. The single lobe, narrow beam has low noise and high power, making it very easy to set the threshold when compared to the competition. In the bottom right section, the single lobe, narrow beam has the added benefit of extending the detection range in 1D time-of-flight systems. Now let's take a look at middle power VCSELs. The RLD85SAY8 and 94SAYQ are 2 watt, 850 nanometer or 940 nanometer surface mount package type VCSELs. The RLD85CHY4 and 94CHQ4 are 4 watt bare chip type VCSELs with 850 and 940 nanometer peak wavelengths. The 2 watt SMD type is available in both clear glass and diffuser types. Target applications are space mapping and gesture recognition. Both can be used as a light source for flash TOF and structured light. The features of ROHM's middle power VCSELs are high power conversion efficiency and good temperature characteristics. The graph on the lower left shows current on the horizontal axis and PCE on the vertical axis, with the lines color-coded by temperature. It is the only VCSEL that achieves an industry-leading 40% conversion efficiency and has very low temperature dependency. Another feature of ROHM VCSELs is that they can be combined with a diffuser to control the spread of light. As you can see in the bottom right picture, VCSELs can efficiently illuminate a specific area without loss. To summarize, ROHM VCSELs are excellent infrared light sources. We have a lineup of products from 6 milliwatts to 4 watts at 850 and 940 nanometers. The 850 nanometer wavelengths are available for indoor use. For outdoor use, 940 nanometers is recommended to avoid sunlight noise. Target applications include proximity sensors, 1D TOF, 3D TOF, and infrared lighting. Thank you for your time today. Please visit our website to learn more about ROHM's product lineup.